Hello everybody and welcome to the first edition of Physics World Live. I'm Metje Durrani, the editor of Physics World, and it's great to have you all here for the first of our new online panel discussions, which we're bringing to you in partnership with the flagship IOP journal, Reports on Progress in Physics. Now for this inaugural event, we're going to be talking about quantum sensors, and I'm going to be handing over to our host for the event, Margaret Harris. And remember, there's plenty of time at the end for questions, so do send them in and we'll try to get to as many of them as possible. Over to you, Margaret.
Thanks, Metje. We've called this event Physics World Live because the plan is for it to be like a live version of the Physics World Weekly podcast and Physics World Stories podcast. In both cases, sessions where we interviewed experts in various fields of physics about their work. The difference is that this time, you get to join in with asking the questions. Our panelists for today's discussion on quantum sensors are Mark Bason and Nicole Metje. Nicole is Professor of Infrastructure Monitoring and Head of Enterprise, Engagement and Impact within the School of Engineering at the University of Birmingham here in the UK. She's the Director of the National Buried Infrastructure Facility, and she co-leads research on geophysics at the UK's Quantum Technology Hub for Sensors and Timing. Mark Bason is an experimental quantum physicist at RAL Space, where his interests range from quantum sensing of magnetic fields to developing next-generation gravitational wave detectors. He's also worked on industrial engagement via the Quantum Technologies Hub for Sensors and Timing and the Faraday Challenge. Welcome, Nicole and Mark.
Thank you very much for having us.
Yeah, welcome. Yeah, thank you.
So one of the many interesting things about quantum sensors is they have applications in so many different environments, everywhere from deep underground to deep space. So I want to start with the underground applications to sort of keep the discussion grounded, as it were. So Nicole, if you could tell us a little bit about the work you're doing in this area. What problem are you trying to solve and how do quantum sensors fit into the solution?
Yeah, it's a really good question because as a civil engineer, I never thought I would get involved in quantum sensing. So if you'd asked me 12 years ago or so, I would have said, I don't know anything about this. This is not something for civil engineers. But civil engineers, like so many other scientists and engineers, have some challenges that we face. And one of the challenges I really work with is to look through the ground. Because even Leonardo da Vinci said we know more about the stars above us than we know of the ground below our feet. And this is still true today. And there's so much in the ground that we can't see. So we have our pipes and cables in the ground that supply us with water, electricity, broadband. We've got tunnel for transportation system, we've got our sewers, we've got foundations. And every time we want to build something, we need to generally dig down and excavate because we need to either put our foundations down there for our new building. So it's not just building up like, I don't know, the Shard, a famous building in London, but we also have to actually look what's below the ground because it's really the foundations that keep these buildings upright and stable. But when we excavate down in the ground, there's all sorts of challenges because, as I said, there's so much there already. And if we damage something or hit something, that can actually cause us a lot of project delays, a lot of additional costs. But there's also a health and safety aspect to it. So we really have to understand what's there. We use a lot of sensors already, but these sensors have limitations in terms of either the cost or the resolution or the depth penetration. And this is where around 12 years ago now, talked to some of my physics colleagues at the University of Birmingham, and they said, well, we do actually have a technology that might be of interest to you. And that's how the collaboration between physics and engineering at Birmingham started to try and look at quantum technology gravity gradient sensors specifically to look through the ground and find things we can't see, basically reveal the invisible.
Okay, so I know your focus is on applications rather than the underlying sensor technology, but maybe you could give the audience just a brief introduction to what quantum system is acting like a sensor for buried infrastructure.
So as I mentioned, the one we're using is a quantum technology gravity gradient sensor. So we're interested in gravity because it's a passive sensor, basically it's a passive technique. We do have classical gravity sensors, which is a mass on a spring. And this spring is attracted by a high density object more than it is by a low density object. So you think of a void, it attracts this mass on a spring a bit less than if you've got a concrete foundation in the ground. And what we are really interested in is relative scanning. But the problem with existing classical sensors is that The spring constant changes over time. It's quite temperature sensitive. So basically, we have to do lots of corrections, a lot of averaging over time with the classical sensors. So the quantum sensor is using a similar principle. So still the sort of Newton's apple idea of an object falling, but rather than having a mass on a spring, we have atoms, rubidium atoms. And the fantastic thing about molecules or atoms is that their test mass is the same today as it is in 10 years, as it is in 100 years. So therefore, we can actually be much less, we have much less drift, and we are much more drift resistant over time. But what's the thing that we are doing with the gradient sensor is that we have two clouds of rubidium atoms. They are trapped in a MOT, in a mechanical optical trap, using lasers in an ultra cold vacuum chamber, and we have them at two different positions. So we use the quantum effect where we give them an energy kick through a laser, then they split into the different energy states, and then we give them another kick and we bring them back together, but in the two different energy states that obviously fall due to gravity, and then we bring them back together. And what we have is a common laser system that interrogates these rubidium atoms in the two different energy states, and then we use interferometry to look at their gradient. But the real beauty is that unlike a gravimeter, whether it's a classical one or a quantum one, it is actually not affected in the same way by common noise sources. So a classical gravimeter is, for example, affected by any vibration, because at the end of the day, it's an accelerometer. So if you've got, so the application I'm interested in is often near roads or on construction sites or near railway, that all generates vibration, but even the wind generates vibration. And even though Birmingham is probably the furthest away from the coast in England or in the UK as you can be, but even there we can measure the ocean waves breaking on the shoreline. But because we've got we're doing the gradient measurement, so any common suppression, any common noise is suppressed, and that's really advantageous because then we can resolve smaller objects or deeper down.
So in terms of the objects you're looking for, you mentioned sort of voids and concrete foundations. What other sorts of underground objects are we talking about? And what are the ones that are most difficult to detect with current technology?
So it's a size and depth variability, basically. So classical instruments that I use as a civil engineer are based on electromagnetic waves being sent through the soil. And the problem there is that you have a depth penetration issue. So it can't go as far down as I would like it to be, because the ground itself, as well as the water in the ground, being a dipole or so, actually affects my electromagnetic wave. And sometimes it can only penetrate a few tens of centimeters. But some of the features that I'm interested in, so our pipes in the UK, so water pipes tend to be at about 1 meter depth. Normally I can see that in a lot of conditions, but also if you've got really clay-rich soil, you can't often see it, especially if it's wet, which in the UK it's quite often wet and we have got clay-rich soils. But you can think of sewers, they are maybe sort of your 2 meters depth, 1.5, 2 meters, 3 meters depth, but also disused mine shafts. So we've got an area in the UK called the Black Country, which is very close to Birmingham actually, where we have quite a lot of disused mine shafts, and they were just poorly recorded at the time. And that's always the problem, that our records of whether it's the pipes and cables in the ground or it's our old legacy mine shafts, we just don't really know exactly where things are. We have got some suspicion, but I was speaking to utility companies, so water companies, for example, and said, what sort of uncertainty envelope should I put on my statutory record data? And they said, well, plus minus 20 meters. Well, that could be in the other street. So therefore, I do need accurate sensors to really know what's there. So the mine shaft is quite interesting, because a lot of these mine shafts that were sort of dug in sort of 1900, 1910, 1920, they have a diameter of maybe 1.5 to 2.5 meters, and they are at a depth of maybe 5 to 10 meters, and they become almost invisible to any other sensing technology I have if I want to use remote sensing, so at the surface. Obviously, as a civil engineer, we're also good at digging, but we do need to know where we're digging. It comes down to where we want to excavate, where we want to dig our trial holes. But yeah, but also I mean, I was involved, I was at a meeting on quantum technology sensors probably about 8 years ago now, where in London, where somebody hit the central line with a pile foundation that they were trying to put through. And clearly you would have thought that we do know where our tube lines are, but again, they are at an age where we haven't recorded it as accurately as we need now for our precision engineering.
That's a good question. I was going to ask also what the potential end users are of this type of quantum sensor. You know, if you imagine commercializing the technology you're developing with your colleagues, you know, who would you eventually sell it to?
It's a question where I want to sell the sensor to or where I want to sell the data to. And I think there is a lot of interest in the additional data, but there will probably be fewer companies who will use the sensor. But the end users who are interested in the data could be all sort of utility companies, water companies, gas, but obviously also network operators. So Transport for London, for example, in the UK. So any tunnels, but also developers and builders, because what we really want to do is we want to use more brownfield sites rather than greenfield sites. And the challenge with brownfield sites is obviously there was something there, but often we haven't built it back to a pristine environment. So therefore there could be old tanks there could be old foundations there, old pipes. We don't know whether they cut off, do they just run through? And trying to de-risk all these sort of developments is really important. So all sorts of house builders could be interested in, but also even as a house owner you're doing an extension or so, there are some areas in the country where you do now already have to use a gravity survey to find old legacy mines. It's obviously not done by the house owner, so they employ a survey company. So there will be several survey companies who will want to either hire the sensor or buy the sensing technology to do the surveys. But I think the interest in the data is enormous.
So what's the status of this project currently? You know, do you have a working prototype? What are some important milestones that you've already passed and what's yet to come?
So probably the biggest milestone has passed, where we had the world's first detection of a underground, what was called a multi-utility tunnel at the University of Birmingham. That was published in Nature in 2022. So the work happened in 2021. So we do have a field-ready prototype that we are taking out for different applications. And we are pushing the envelope at the moment in sort of what's the art of the possible of the current sensing technology with the current sensitivity. Obviously, my physics colleagues are trying to also look at the SWaP-C. They are trying to also increase the bandwidth so you can operate on more what I call mobile platforms. So whether they are cars, whether they are vans, whether they are drones, so that you can actually operate them in other environments, because the classical sensor is a stationary sensor. So I do point measurements and I have to be in one point for quite some time. But what we really want to do is increase our bandwidth so that we can actually do this on the move, and we've seen that. So it's trying to really look at what's detectable, what can we do, what's the sort of, how would we actually, what's the survey methodology? So that's one aspect that we're really working on as well. So it's not just the sensor development, but it's also how do we then put it into practice and how would we operate the technology? Because again, at the moment, you tend to do a grid survey. So if you don't know what's there, you do a reasonably regular grid. If you have an idea where the feature is, you have a higher densified grid locally and then have it lower densified a bit further away. But if you don't know anything, you have a more or less regular grid. So we're trying to look at processing methodologies as well, where you can actually optimize that survey. So you're not using a regular grid, but you can actually home in on the feature of interest.
And final question for you, what's the potential impact if you and your collaborators can get this technology working? You know, paint me a picture of future civil engineering projects that's conducted with the help of quantum sensors.
That's quite a challenging question, because for me, a quantum technology sensor is another important tool in my toolbox. It's not necessarily the silver bullet, so it won't solve all my problems, but it will solve some of my problems. So, for example, in the UK, we the cost of damaging utilities to UK PLC, to the country, is around £5 billion a year. So just imagine we could shave off a fraction of that. That could be a saving. There is a lot of, what we haven't talked about is all the excavations we tend to do in the wrong place because we don't know where the buried pipe or sewer is. So we dig big holes, that causes lots of traffic jams. So if you add all this together, there's quite a lot of several million or billion pounds of GDP that you could contemplate because people are not stuck in traffic jams. And if you add all that as a cost to the person and then to the country of effective work lost, you can very quickly get really high numbers. And then there are obviously other applications. So the one thing I haven't talked about is the sort of more the natural science aspect. So one of the projects I'm currently leading is to actually look at groundwater and to look at aquifer and to look at recharge of aquifers. So this would then help with our water security and to ensure that we don't draw down our aquifers too low. We always allow enough recharge. But also one application there is also to look at pipe leakage. So if we don't lose so much water into the ground, again, that's good from a sustainable development goal, if you think about those, but also clearly for the country and hopefully also for the end user, because we're not paying for water that's just lost into the ground.
Yeah, wonderful. So a future in which we have fewer streets torn up by construction works that didn't need to happen because they were happening in the wrong place, and fewer leaks of sewage into our rivers. Excellent. What's not to like? Mark, I want to bring you into this conversation now. So I understand you're working on several quantum sensing projects at the moment, but I want to start with your work on gravitational waves. Maybe you could just begin by reminding our audience what gravitational waves are and why we're interested in detecting them.
Well, great. Yeah, I think Nicole's done quite a lot of the heavy lifting on that because she's explained about atom interferometry. That's a really good start. And so gravitational waves have been detected already in high frequencies. So you may remember LIGO and Virgo collaborations doing that. And so they have ripples in space-time, which is the easy way to think about it. So it's space-time expanding and contracting with different frequencies. And so what we want to do as part of the AON collaboration, which is the Atom Interferometry Observatory and Network, it's a UK collaboration, we want to detect gravitational waves in the decihertz regime. So that's a bit less than 1 hertz. And you can think of this like the early days of astronomy, where you had some types of telescopes for the visible. So let's say Galileo with his new telescope. But then there's obviously been an explosion in astronomy over the hundreds of years since then, where people have looked at, let's say, the UV or ultraviolet or radio waves. And so if you can look at gravitational waves on different points of the spectrum, you can be sensitive to different events. So in particular, decihertz, that can play into studying the evolution of supermassive black holes. So you can study intermediate mass black holes, and then that should give you some clues about what's happening at larger scales.
Okay, so I love I can actually ask this question because 10 years ago we couldn't even detect gravitational waves at all, and now I'm already asking how to do it better. But how do we currently detect gravitational waves, and what are the drawbacks or the limitations of doing it that way?
Yeah, so as I mentioned before, they have been detected at these higher frequencies, and that uses laser interferometry. So that uses light, and light basically, which you can send on 2 different paths, and then you can recombine them and interfere them. And so just like waves interfere in the ocean, you can get peaks and troughs, and then you can use any changes in that interference to detect very small length scales. So that's what they do currently using light. They are kind of taking advantage of quantum technology for something called quantum squeezing. So that's to get lower noise operation. But what they can't do is go to these lower frequencies that I talked about. So there it gets very difficult at the moment to be able to do that. So there are plans to try to get down to this decihertz using light. So it's a little bit of a competition at the moment between who's going to have the best technique to do it, whether it's the light or the atoms. So yeah, we'll see in the next couple of decades who wins.
Tell us a little bit more about what your proposed alternative is and how it works.
So we're not going straight towards an instrument that will be able to detect gravitational waves. We have a sort of stepping stones along the way. So to detect them, you'd need something like a 100-meter long atom interferometer. So it's the other end of the scale from what Nicole was talking about, these portable things where you can put them on the back of a truck or something. Yeah, it's very hard to put 100-meter detectors on the back of a truck, and you need that long baseline, it's called. So that's how far the atoms can fall. You need that because the sensitivity goes with how long you can let the atoms fall for to the square power. So that's the t-squared effect. So the longer you can let them fall, the better you can get, and then you can really improve the sensitivity. So then the obvious destination to work towards is to go into space, so that way you have microgravity, and then you can let them fall for obviously a very long time. So that's kind of one of the reasons why I'm sitting in RAL space at the moment, to be able to progress towards those kinds of measurements. But yeah, the first step is a 10-meter detector, so we hope to build that at the University of Oxford. There's a stairwell there, so they're one of the Aeon collaborators, and then move towards 100-meter and a kilometer. So then you kind of run out of places where you can put a kilometer-long tunnel. So mine shafts, so we're returning to Nicole's, what she mentioned before. So we're looking at places around the world where you could build a 1 kilometer long detector, but there are a few challenges to go before we get to that.
What are some of the challenges you need to overcome, technologically speaking?
So just making a long baseline atom interferometer is pretty difficult, actually. So the stability requirements for engineering friends, especially at RAL, are pretty tough. So you have to control that. You have to do it in an ultra high vacuum, of course, like Nicole mentioned previously. So lower pressure than space, so 10 to the minus 11 millibar for anyone who's interested in the actual numbers. Margaret may recognize those units from some time ago. You have to control magnetic fields, and we want the beefiest, most powerful lasers with a very narrow line width, so a very precise color to be able to interact with the atoms that we're using.
So are there any differences other than the size and the requirements and technological requirements between the ground-based interferometer that you're building as a test case versus the possible future space-based version?
Let's see. So the ground-based ones, we're using strontium, so that differentiates it from the rubidium ones that Nicole mentioned. People have plans also to put rubidium interferometers into space, which is another sort of topic, another application. Strontium is a bit of an awkward element in that it's not as simple to use laser cooling techniques as it is for rubidium. You need more lasers, and you need to be able to stabilize their frequency very accurately. So there are complications with that, and obviously putting things in space, you kind of want to minimize things like power consumption. So there are challenges there to sort of tackle, but that's why we're here, right? It's to do the interesting stuff.
So in that case, what's the advantage of using strontium for the ground-based version?
So that's a very technical argument about laser phase noise, which we can go to if you want, but it's related to being able to use one laser beam which interacts with 2 clouds. So in this gravitational gradient configuration, and you want the phase to be defined of the laser pulse that's emitted at one point. So you don't want to use 2 laser beams, which you do for rubidium. So it's all to do, yeah, with the phase noise.
Okay.
Technical details, Margaret, I'm not.
Yeah. Well, we'll have some audience members who will absolutely lap up the technical details. Yeah. I want to turn on to one of your other projects now. I know you're also working on Rydberg atom sensors for measuring specific radio frequencies. What's that project about? Again, maybe you'd introduce what a Rydberg atom is in the first place.
Yes, okay, yeah, that's really quite different. So that's for the purposes of Earth observation, first of all. So a Rydberg atom is an atom where the electron has been excited to a state that's very far from the nucleus. So the elements we use there are like rubidium and cesium. You have just a single atom orbiting the nucleus. So it's a bit like a hydrogen-like atom, it's called. So they live with some principal quantum number, which is quite low. So typically it's about 5 or 6 rubidium or cesium. And so if you use laser beams, you can excite that up to a higher energy. So something like 20 or up 50 or up to 100, and then you've moved the electron very far away. And because it's far away from the nucleus, it becomes more sensitive to electric fields. So they can perturb the energy of that state. So people have been sort of investigating these for the last decade and a bit, I suppose. And now they've developed techniques where you can study or you can measure electric fields all the way from DC up to terahertz. So that's what, 12 orders of magnitude or something crazy like that. And so we are about to start a project with Durham University through ESA, so the European Space Agency. And what we want to do there is find out whether we can build something called a radiometer. So that's a type of instrument where you can study part of the black body radiation spectrum of the Earth. So you can look at the Earth glowing about room temperature, let's say, on average, and then you can measure specific frequencies. And one of the things people like to look at is the salinity of the ocean. So there's a resonance around. Oh no, I should probably remember the number, but it's about in the tens of gigahertz that you can use to study salinity, and then that can inform models for climate change.
Okay. And what are some other applications to be able to sense that sort of radio frequency apart from sort of Earth's observation?
So people use terahertz for non-destructive interrogation. So colleagues in Durham have been leading this. You can also think about communication, so maybe inter-satellite communication at higher frequencies. Maybe you can get higher bandwidth if you do that. So it's a little bit of a thrust from the quantum communications side of space to be able to use optical comms, so to point laser beams up and down at the Earth or between satellites. But there's still, I think, quite a lot to be done in between sort of radio frequencies and light frequencies. So terahertz could be used for that.
And the final project I want to talk about, I know you've been involved in projects that use quantum sensors to detect magnetic fields. Can you tell us a bit more about that application?
Yeah, we can. So we've got a few projects along that line. We've got one which is with British Geological Survey and the University of Strathclyde. And there we're interested in developing magnetometers that go on the ground, but are used to measure the changing magnetic field. And so that's interesting for space weather, so the impact of the sun on our environment. So related to Northern Lights, so it was in the news a few months ago now. So if you can measure it at more points in the UK, you can increase the spatial density of your measurement sites, and you can build more accurate and more local models. And that's important for things like ground-induced currents, which maybe Nicole can sort of identify with. And so if you can model these and predict them, you can work with people like National Grid to say whether there are any risks to, let's say, substations or transformers all over the UK. Because in very severe weather, space weather events, you can get these things burnt out and knocked out, and then not having electricity across the UK is a little bit of an issue. Yeah.
And what about medical applications? And we've got a question actually from the audience. So, is it possible to use these detectors to map the workings of a single cell or detect faint brain activity?
Yeah, so I also worked with magnetometers and came into contact with a few neuroscientists across my time. So you can use magnetometers which are configured to work in low fields, in sort of low noise environments. So this is work that was sort of pioneered at the University of Nottingham. So that's a process called magnetoencephalography. And so what they do there is they place hundreds of these sensors across the skull, and then they look at brain activity and try to locate where in the brain the neurons are firing. So that's for whole head. And that's an adaptable technique, so you can use that to study infants and look at things like epilepsy in young infants. And then in terms of single cell stuff, you can use something called nitrogen vacancy magnetometries. So that's a type of defect in a diamond, and you can use that type of defect also like an artificial atom, and you can do magnetometry with it. And there you can get resolutions which are much better than you'd get with the types of magnetometers that we're developing here. So they're not as sensitive. So we're interested in sensitivity and precision, especially. But they are very small and they can get very close. And in cells, that's kind of what you want them to do.
Okay. Well, we're now at the halfway point through our webinar, so I want to open these things out to both speakers now and start asking some questions that hopefully both of you will have things to contribute on. Kicking it off, one of the reasons we chose quantum sensing as a topic for this first edition of Physics World Live is that despite the exciting applications you've both talked about, quantum sensing usually gets only a fraction of the attention and hype devoted to other areas of science, quantum science and technology, specifically quantum computing. Why do you think that is? I mean, these are exciting applications that could, really do some amazing things in terms of scientific discovery and practical applications. Why does it get so little attention? Nicole, you want to start?
Oh, thank you. I was hoping Mark would have a comment first, but I think it's quite. I find it quite difficult because obviously being a civil engineer, I'm not as embedded maybe in the sort of broader quantum community as Mark is. So from my viewpoint, I always think it is really quite interesting because we have got, Mark talked about the work that Nottingham's doing, and they've got prototypes out, they're working with clinicians, they've seen real advantages of using the magnetic sensors on children, and the advantage there being that they can be that they don't have to hold still in the same way as they have with classical devices. So again, we can reveal something we couldn't currently do at the moment, and we do have these prototypes. We've got spin out, so I think we are getting, it's almost on, it feels a bit from a bit of an outsider from a sort of engineering viewpoint. That's a bit on the cusp now, where we're actually getting these products out to market because we've got these spin out companies. We're using them as products. The same is true with the quantum gravity gradiometer at Birmingham. So that we are seeing these now coming to market, and I think we're then seeing the advantages. I think I don't know, to me it feels that the hype on the quantum computing is around the sort of long-term potential. When we really get quantum computers with a certain number of qubits, then I guess they could also revolutionize some ways of doing things because of the processing power. I think in general in the UK we've been reasonably lucky, if that's the right word, I think there has been funding across the spectrum, so not just on quantum sensors, not just on quantum computing, but also quantum comms. So there are different aspects, and so I think there has been a reasonable amount of money for different areas. So I don't think it's quite as one-sided as what you implied in your question. That is, but I think quantum computing maybe is a bit more sexy than looking below the ground for my application area. I mean, we try to normally hide things in the ground, things we don't want to see. So our pipes, cables, we don't want to have them all. We don't want to have pylons in the back garden. So maybe that's not so sexy. And maybe quantum computing is. I don't know. Don't know what Mark thinks.
Yeah, Mark, you go for it.
Yeah, I'm not sure if it's such a bad thing, because it's not really that there's a limited number of quantum physicists and we have to divide them all up, and some go to computing and some go to sensing. I think computing was attractive to me as an undergraduate and probably got me interested in quantum physics in general. So I'm hoping that there's going to be a little bit of let's say exchange of ideas between the different fields. So hopefully the growth of quantum computing can generate some extra skills and extra techniques that we can bring into sensing. So like the Rydberg atoms in particular, there are ways that some of my colleagues at the National Quantum Computing Centre want to use Rydberg atoms in tweezer arrays. So this is done in Strathclyde as well. John Pritchard has been leading this in the UK. So yeah, maybe slightly sexier, as Nicole says, but hopefully it's to the benefit of the wider quantum community.
Okay. A question from the audience for Nicole now. Two-part question. Can this technology be used to detect such things as mines or old bombs? We get a lot of unexploded ordnance, both here in the UK and in various parts of Europe, due to the sort of area bombing that happened in the Second World War. Of course, there are other more recent conflict zones around the world. I could see this being having a need there, but can this application solve it?
Depends. As a geotechnical or engineer who deals with the soil, that's a classical answer. It depends. What the technology I'm involved with, what we're looking at particularly, is a density contrast. So if the more modern surface mines, they are made out of plastic, a lot of it is plastic, and so therefore the density contrast between that and the soil is not as great. The older ones you can probably detect, and indeed we've got a PhD student, it's a colleague of mine supervising a PhD student who's specifically interested in ordnance, unexploded ordnance, and I think you can, but it's probably a sort of sensor fusion, data fusion. So again, it's not just one sensor in its own right. Obviously, with a lot of things in the ground, especially with unexploded ordnance, you want to be absolutely certain you know where it is, and you know where it isn't. Probably as important as knowing where things are. So therefore, if you use multiple sensing technologies, not all quantum, can be classical sensors as well, and therefore you improve your confidence that where things are or where things aren't. I think that's really useful, and it could be used for that. So yeah, it can be. The other question was on mine shafts, or mine working. So yes, exactly is what we're trying to do. It comes down to, again, this compromise of size versus depth. So gravity trials off with 1/r², where r is the distance to the object from the sensor, and gravity gradient is 1/r³. So the deeper a feature is, the bigger it has to be. I mean, it also depends on the sensitivity as well, but in general, the deeper it is, the bigger it has to be. So if you think about a cone, a sort of sensing cone, so the deeper you go, the bigger the object has to be. So yes, you can find mine, and we've done something with the Coal Authority in the UK to look at old disused mine working, so not just the mine shafts, because again, 1900, 1910, 1920, the directions of mines were not recorded as well as we would like them to be. So yeah, we can find it, but it all comes down to density contrast, a lot of it for the gravity sensor.
Okay, and another question actually for both of you about miniaturization. So Nicole, you mentioned that it might be possible at some point to put this technology on a drone. Mark, you talked about the incorporating magnetic sensing technology into clinical practice. What are the challenges of making these systems small? Mark, you want to go first?
Sure. I guess there's the general problem of getting lasers, I suppose, which probably every atomic physicist will say is an issue. You want reliable, sort of very small-scale lasers that are typically people use VCSELs, vertical cavity surface emitting lasers, and getting those to behave nicely is one trick. Then there are kind of limits on the type of system your atoms are held in. So there's, I guess, a general classification of cold atom systems versus warm atom systems. So that's to do with the pressure inside the cell, or vapor cell normally. So that can have an influence on the performance. So in vapor cells, you can have decoherence because your atoms are hitting the walls of the container, whereas in cold atoms, you typically don't want your cold cloud to hit the walls of the container at all. So depending on your application in the cold atom side, you want to leave the cloud to expand for some time, which is let's say in the satellite version would be in free fall. Your cloud would be expanding outwards, and so depending on what temperature you can get to dictates how big that cloud will be after a certain time. So then there's a match between what temperature you want to get to, how long you want to measure for, and therefore what type of vacuum vessel you want to put things in. So for stuff on the ground where you don't have the advantage of microgravity, then it's probably likely that you can get significantly smaller. So For the vacuum cell, let's say you could incorporate everything together, you could probably be looking at sort of less than 10 cubic centimeters or something like that for the sensor head.
Something you could put on, fit in a room rather than an entire laboratory.
Oh yeah, and I think we've moved quite far along that way at the moment. So we'll be looking at fabrication, nanofabrication techniques, I guess, in the next few years to try and to squeeze that down even further.
And Nicole, talking about possibly putting this technology on a drone or some sort of super mobile device as opposed to the back of a lorry.
Yeah, I think Mark mentioned a lot of the sort of technical challenges when you try to miniaturize it. From a gravity gradient viewpoint, it's also the distance between the two atom clouds. So the closer you bring them, the less sensitive your instrument is, because the longer your baseline, the better it is. So the current instrument we're using has a sensor head, a tube, a cylinder, a tube that is around 1.8 meters, maybe a bit less, 1.7 meters. I haven't stood next to it for a while, so I can't quite remember, but it's in that sort of ballpark figure. But as a civil engineer, I've got a drill rig on site that is 3 meters tall. So therefore, I'm not so worried if I want to take it on site. But if I want to get it into a borehole, then clearly I need to shrink it down, for example. And there might be some advantages why I want to not just measure from the surface, why I want to actually measure from inside a borehole radiating out. So there are all sorts of issues. But I think it's horses for courses. So I think it doesn't always have to be the smallest system. Clearly, if you want to have it on drone, you have to think about the weight and you have to think about the form factor. But there are certain applications, certainly in sort of my area, where it's less of a problem. The problem is more the robustness. So can it cope with the construction noise? Can it cope with the weather? Can it cope with the sort of the ground, the mud? It's not a optical table environment when you go onto a civil engineering site. It is a lot dirtier. So can it cope with this? So it's the ruggedness that's probably as important for a lot of my applications as it is the form factor.
And a question from the audience now. How would you compare the technological readiness levels of quantum sensors compared to quantum computation or quantum communication? Too many quantum words, sorry. How long will we have to wait to see the benefits from quantum sensing compared to those promised by quantum computing or quantum communications?
Well, I think Nicole mentioned earlier that we're already seeing the benefits of some quantum sensors, particularly in the brain scanning type of work. So that's now. So now, then I think you really have to go application by application to say how far away they are. So the gravitational gradient, Nicole also mentioned, I think is also progressing to sort of commercial product sort of style. Then the applications, let's say for Rydberg sensors, are probably a few years behind that. And the magnetometers are also progressing. So yeah, compared to quantum computing, I think we're, I don't want to say a number, but probably at least decades ahead of them, let's say. And then quantum comms is probably somewhere in the middle. So there have been satellite missions demonstrated. So Chinese have a QKD mission that's up there, and so my colleagues are also trying to do a CubeSat, which is a very small satellite-based version. So that I guess then in the next 5 to 10 years might sort of progress towards a quantum communication system, maybe for banks or for sort of very crucial healthcare data or something like that.
Nicole, anything you want to add?
No, I think Mark has covered it all. I think I mean, as Mark said, certainly the brain scanning is, I think, in the clinical trial phase. The quantum gravity gradiometer has got a spin out. They're trying to sell the initial products. You've got MEMS gravimeters that have been developed alongside that are probably also at commercialization stage now, and they are sold around the world. So I think we won't have hundreds of sensors in the public domain, so to speak, so in end users' hands. But I think there will still be a lot of demonstrations, and they actually highlighting the benefits of the data, not just the sensor itself and how the sensor works. I think both Mark and I are involved in many projects where we are actively engaging with end users, and they are actively involved, and they were involved quite early stage, probably earlier than you might expect with some of these end users. But I think that's benefited the sensor and timing community because they have their feedback loop directly. And what we're hoping to avoid is what happened in the civil engineering environment with ground penetrating radar, where there was quite a hype many years ago, sort of in the sort of 60s, 70s, and everybody said it can do all these things, all these wonderful things, and then it was demonstrated that it couldn't or it didn't do it, which was partly an application error, so how people use the sensor, but also partly a too much hype. And I think we have learned from that, and we've done it quite differently, and that's why we've engaged with these end users so early on in the various phases of the development.
Talk to me a bit more about who those end users are that you've engaged with. This is actually a question for both of you.
Well, I do it from my side because that's obviously a lot easier. You've got the likes of BT, and so these tend to be UK companies because obviously that's where we're based. So BT, so British Telecom, Network Rail. You've got different water companies. So for those who don't know, the UK is privatized. So we've got 26 water companies alone. So some of those have been involved quite actively. Survey companies, we've had probably about 5 or 6 survey companies. So those are companies that do use a range of traditional geophysical sensors at the moment, including classical gravimeters, and they want to get to know how quantum sensors work. We've had the likes of BAE Systems. I think I need almost a slide with all the logos in front of me, but if I ask the principal investigator of the hub, I think it's something like we've engaged with something like 120 different companies, ranging from all different areas, but also obviously a lot of sort of component manufacturers, like laser companies, vacuum companies, so all those who make components as well, not just the end user. So lots of different organizations to really have the full supply chain. So from those who produce components to those who might produce or want to produce and license the actual sensor itself as a package. And for those who then want to maybe hire it or buy the sensors and use it and are most interested in generating the data.
And Mark, for you, I mean, one of your main end users is actually other physical scientists, astronomers, astrophysicists. How are you working together with them to ensure that what you're doing is building something that will be of interest to them?
Yeah, so we try to have community-based workshops. So we had one last year, in particular about gravitational wave noise sources. So we're trying to learn, especially from the light interferometry people, and engaging gravitational wave sort of experts. So that's one way, I guess. Just the traditional way of publishing and having your work up for scrutiny is the other way. And so yeah, we're progressing towards sort of full noise models of one of the AON systems. But then otherwise, producing the data from interferometers. There's also work with ESA, which is looking at generating new missions for gravitational measurements of the Earth. So there, again, a bit like Nicole's example, if you're looking at aquifers, then doing that from space has advantages of, let's say, long observation times. You can build up very detailed models of the Earth. Then you can look at movements of water across the Earth and look at water cycles and then predict, hopefully, whether there may be issues in the future. And so that kind of data generation, I suppose, it's not the interest of humanity, I suppose, that isn't in the commercial domain. So that's partly why ESA is interested in this work. So end users great in the commercial world, that's great, but then we should also remember sort of non-governmental and other sort of scientists as users. Yeah.
And now from the audience, so a more technical question for Nicole. You mentioned that what you measure is the density contrast between the soil and the object you're looking for. How does the procedure work to determine what object you're measuring? Do you have predetermined models that, for example, if there's an underground foundation, then the interference fringes will look like this, versus if it's a water pipe or, an electrical cable, it's going to look like that? How do you tell what you're looking at?
If only it were that easy. No, so a gravity sensor, doesn't matter whether it's a classical or a quantum sensor, measures an average value, or measures a sum of all the gravitational, the microgravity, the gravitational field, in theory, to the center of the Earth. And it gives you one value, and then obviously you measure, you basically end up building, it could be a contour map, but you've got, for your measurement points, your grid, you get data. And you then have to interpret it. So you have to use something called inversion. But the problem is this is non-unique. So what this means is if I have a small void close to the surface, that will potentially give me the same signature as a larger void a bit further away from the surface. So then you have to do some clever post-processing to try and determine what the object is, or what it could represent, and it can be multiple solutions. This is again where multiple sensors come into play, where you're trying to actually set some boundaries. So if I could use, for example, ground penetrating radar in combination with gravity sensing, the ground penetrating radar should be really good for measuring things close to the surface. So when I say close to the surface, for me, that means maybe within the top half a meter, maybe a meter, depends on the soil. But then I can actually rule that out, and I can actually take that into account in my inversion or my post-processing. If I have an inkling of what it might be, so if I know there's a mine shaft somewhere, then I can also do some forward modeling. So I place the mine shafts at different depths, different diameters, different positions, and try to almost match my forward model with my measurements. With the inversion, I can use machine learning and AI as well. I know that's in everybody's hot topic at the moment, but what it allows us to do is obviously generate lots of different scenarios and really get the system to also learn what it looks like if you have certain types of features. But it is difficult, and it's not trivial at all. So developing the sensor is one element, but then actually doing the post-processing for me is a real challenge as well. And that's not something we're overlooking. We're working actively on that side as well, because without it, it would just be a whole lot of data, but it's the interpretation of the data that we have to worry about. And it's very different to a lot of the active sensors that I use. So I mentioned ground penetrating radar before, and I said that it's an electromagnetic signal that I sense through the ground, and it's basically a reflection I measure, and I measured time travel basically. And that's a lot easier. That if it's a clear signal, and in the nicest world, if I'm looking for a pipe, it looks like a hyperbola, and I can spot exactly where it is. There's still also challenges, so it's not quite as trivial as I'm making out, but it's a lot easier, or can be a lot easier than gravity. So yeah, it's not that a certain the sensor itself is almost innate of what's there. Basically, it just measures the gravitational field, and it's then the interpretation that tells me what it might be.
Okay, so I know, Nicole, you're an engineer by background, and Mark is a physicist, but as we've seen with both of your presentations, there's really a need for the skills of both groups of people to come together. How does that work for each of you? How do the skills of engineers and physicists contribute to your respective projects? Mark, you want to start?
Yeah, I can. So at RAL Space, we've got many decades of experience in developing space missions. So we have an engineering sort of cohort that goes from mechanical, software, optical, radiation, thermal, all these, I guess, more engineers than I thought existed before I came here. And getting used to, I guess, mission development and engaging these people at the right time is very interesting. So being around them, learning about how they work, what they do, what their assumptions are, is really good, because then it can inform some of the developments, some of the quantum physics that we try to use to develop better sensors. So here I think it's a very good mix of different disciplines.
Nicole, you mentioned at the beginning that you had never expected to be thinking so much about quantum mechanics as a civil engineer. How's that collaboration been working for you?
I think it's really exciting because obviously what scientists and engineers have in common is that they're curiosity driven, they want to solve problems. And so therefore, I think the biggest challenge initially was to really work out on a, dare say it's not common language, but understanding each other's language, because while we use the same words, they mean something slightly different in the different communities sometimes. And it's really trying to understand each other so that we are comfortable in working each other's sort of sphere and area. And it's really moving from sort of just working multidisciplinary, which to me is just working alongside, each base is still being based in their discipline, but then moving to transdisciplinarity working, where we really move into the other disciplines. So I could have had some of my colleagues from the Quantum Hub being here today and probably talk as comfortably about what's below the ground and where the challenges are and what civil engineers find difficult. I wouldn't say I'm quite as comfortable of giving you the whole ins and outs of a quantum technology gravity gradiometer, but probably enough to provide a lay audience, give some summary or so. And generally, when we have any politicians coming to Birmingham or so, it's generally they ask the civil engineer to give an explanation of how the sensor works with all the physicists in the background, which is generally quite fun. But I think it is looking at having different viewpoints, just bringing different environments to the problem. I think has really made a difference of really. So from my viewpoint, I really know how surveys are done on site. So what's the challenge on site, and really bring that in very early on. But also we've got electrical engineers, we've got mechanical engineers really looking at the swap-C, looking at the components, looking at the more things on the chip or so. So having it, miniaturizing it or so, but also the control system, because at the end of the day, for my world and my environment, for these sensors to be useful in that environment, I can't have a quantum physicist or quantum mechanics next to me. We need to be able to hand it over to people who are used to digging holes, in essence, who are used to running an excavator or so. So it has to be at a I think the technology has to be such that the control system is really quite important, and that's probably more in the electronic engineering side. But we don't compartmentalize it like this, so we're not saying, oh, you're working on this, you're working on that. I think it's the collaboration that really makes the difference, and I think this is what Mark was hinting at as well at RAL. Also having that collaboration between different disciplines is really what makes the difference.
Thank you both for a wonderful discussion. I think that's probably all we have time for today. Is that right, Metje?
Yeah, so thanks very much, Nicole. Thanks, Mark. Thanks, Margaret. And thank you, very much for joining us for this very first Physics World Live, and also to our partner, Reports on Progress in Physics, and our sponsor, Hubner Photonics, for their support. And of course, thank you all in the audience for coming along. That's been great. The next event in the Physics World Live will be on the 26th of September, and we'll be focusing on the future of particle physics. It's the 70th anniversary of CERN this year. And also we're talking about battery technology on the 21st of November. So thank you for joining us for our very first Physics World Live, and please do join us for the next two events this year. Thanks again. Bye-bye.
Thank you. Bye.
Thanks.
Thanks.